I have here a tennis ball on a string. Now this tennis ball has been cut open and a battery put inside, and it has a little buzzer. Now when I turn the buzzer on, it makes a noise. Quite irritating. But I want you to know something about this noise. Because of the speed of sound in air, the frequency of this sound produces a wavelength that is fixed. And it doesn't matter whether or not you hear it from here, or from here. The only thing that should change is how loud the sound is. Because for a fixed speed, the frequency produced by this buzzer is going to produce a constant wavelength, longitudinal wave towards you. So if I have my buzzer here, the source of the noise, then those ripples of sound are going to be like ripples in a pond. They're going to indicate the presence of a wave front, or like the peak of the wave moving away from the source. And drawing this, I'm trying to draw concentric rings like ripples in a pond. And so it does not matter if I am listening here or if I am listening there, it always sounds the same. And that is because the wavelength here is the same as the wavelength there. That's with concentric rings, it's the same radius all around. As the sound spreads out, it gets quieter, but nothing changes to the pitch. Nothing changes to the frequency or the wavelength of the sound as it spreads out. But what happens if this source of sound is moving relative to me? Then what we will observe is not just a change in the volume, but also we might observe a change in the pitch of the sound. And let me demonstrate. So what happens if this source of sound moves relative to the person listening to it? Now we can investigate. So what I'm going to do is I'm going to take the sound over here and I'm going to come towards you as fast as I dare. Okay? So as soon as I'm at a reasonable distance, I'm going to turn it on and I'm going to move towards you, and then we're going to see what happens. Now, one thing that you will have noticed is it certainly got louder as it approached. But did you hear something interesting to do with the pitch? The actual pitch, the note of this buzzer changed when I went from moving towards you to the point where I was behind the camera, moving away from you. Now, I'm not really moving fast enough to observe a large change of pitch on here. But there is something that I can do to make it more obvious, and that is swing it around my head. We need a little bit more space to do that. So, I'm going to put my thumb through this knot because I don't want to lose the thing. And what you'll notice is that sometimes the ball is right over there, much further away from you. And so it's going to be quieter because the sound drops away with distance. Obviously things in the distance will sound quieter than things nearby. And the ball is going to be much louder when it comes past you. But the bits that I want you to try and discern are the points when it's here and here. Because when it's here, it's moving towards you. And when it's there, it's moving away from you. And you may notice a change in pitch of the ball. Let's give it a go, shall we? Alright. Started on a short string. Here we go. Now to me, it sounded at the same pitch. And to prove it, I'm going to bring the camera into the centre of the circle. I'm not even going to cut the footage. I'm going to just bring you in, and you're going to get my eye view to show that from a different perspective, that sounded all one pitch. Okay, here we go. Now, wasn't that different? Let's explain why. So what is going on? Well, as I stood there, whirling the thing around my head, there was a moment where the thing was moving towards you, and there was a place where it was moving away. So I want to consider this situation first, where the object that is emitting the sound is moving towards the person observing it. Now, if this is the object, we'll draw it again. And I'm going to draw the person hearing it over here. Now, I'm going to draw the person hearing it as like an ear, because otherwise you draw the observer as an eye, but it doesn't seem right if we're doing a sound. And at this moment, the speaker is moving towards the observer. Now, because sound travels at 340 meters per second, between each pulse of the longitudinal wave, the ball has actually moved a little bit. It's crept back up on the released wave. And then the next one is released and it creeps back up. And then the next one released. And it means that in front of the ball, the wavelengths have been caught up with. And the ball has actually left and produced a greater distance between the wave peaks on the receding side of the ball. It's run away from those waves that it has emitted. And so what it actually does is it produces waves that are more like this. They no longer are concentric, but in fact they are scrunched up in front and they are stretched out behind. So if I am listening here, I get a series of waves that have quite a small wavelength or quite a large frequency. And that means that when the ball travels towards you, it should be quite high pitch. If you are on the other side of this, and the source of the waves is travelling away from you, then what you are getting is waves that are quite long or quite low pitch. And this is what Doppler discovered. Doppler realised that as a source of a sound moves towards you, it sounds high pitch, and as it recedes away from you, it sounds low pitch. And this is why it's because of the waves that are being produced. Now, in real life, we see this all the time with police car sirens as they drive past, race cars at a Formula One circuit, train whistles. That sound of a race car going by, that is the Doppler effect. Right? High pitch moving towards you, low pitch moving away. Even the aeroplanes as they fly overhead, they're like, and it changes the pitch as it goes over. This is the Doppler effect, and it is really clearly audible as soon as you're listening for it. Now, here's a very interesting thing. You see, it's not just sound that can have the Doppler effect. Anything that produces waves of any kind, if the source of the waves is moving, then you will observe the Doppler effect. Now, you might be curious about whether or not light does this. Well, there is a major difference. Light travels, to start with, at 300 million meters per second. And travelling at that speed means that an object has to be moving really fast before we observe any scrunching up of the waves at all. But indeed, it is true that if you travel fast enough, that things that would normally be white would end up with their wavelengths squashed together as they move towards you, making them appear slightly blue. In fact, an object that was red would look blue if I travelled fast enough. It actually means that if I go through a red light fast enough, it would actually appear to be a completely different colour. So something red, if approached fast enough, would appear blue. Oof! Ah, yes. Good. Now, astronomers realised that if objects moving away from us have their wavelength of their light stretched slightly, that they should appear slightly more red than an object moving towards us. And this is indeed what an astronomer called Edwin Powell Hubble discovered about 100 years ago. He looked out at distant galaxies and he found that they all looked more red than was expected. And this was the first major piece of evidence that all of the galaxies were moving away. Strange that. Evidence that the universe was expanding and evidence for the Big Bang itself. Ooh.